Good morning friends. Today we are going to discuss on a stability of bicycles. Someone says, why can you stay on a bicycle when moving but not when it's standing still? So you might be getting the answer of these questions in this lecture series. You think of something like a table or a couch. It has a four leg that touch the ground floor and form a base of support. As long as the table or a couch center of gravity is above this base of support, it will be still statistically stable or stable when at rest. But you look at the other end on a bicycles. A bicycle is having only 2 points of contact with the ground, so it is statistically unstable, and bicycle's base of support is a line segment because it only join the 2 points at the base. So when you join these 2 points, it become the line, while in case of the table or a couch, it has a 4 points, so it can be a polygon. So a good base of a support needs at least 3 contact points with the ground. So bikes are hard to keep upright when they are still. But if you are taking the case of tricycles, good tricycles having the 3 point of contacts. So where it can form a triangular baselines and which can be a stable even though they are still. So balancing a bicycle is possible at rest only with special techniques known as the track stands, but it is easy when moving forward. So you look at the figure, cyclists keep a bicycle stable with the help of track stands, where he slightly turn his steering wheels towards the left or right to make the balance. Like you can walking on a stilts, balancing a bicycles derives from an ability to steer the support points to a positions under the center of mass. This keep a bike stable. Many bicycles are capable of making the necessary steering adjustment automatically without any rider's input, that we'll see in the coming slides. Unfortunately, the mathematics propagating to describe a bicycle motions and self-stability difficult and have to be validated experimentally, so design guidance remain highly empirical. Common misconceptions or a perhaps oversimplification is that the gyroscopic effect of the wheels make a bike stable. Gyroscopic effects do a play role in bicycle stability, but it is relatively minor, particularly at low speeds. Many stable radial bicycles with little or no gyroscopic effect have been built and they checked for the stability and prove also. Consider the foldable scooters that have been popular with the children and students in the recent years. These two-wheeled vehicles have very small and light wheels. The angular momentum of this wheel must be extremely small compared to a bicycle and almost negligible. Yet they are easily ridden even at a low speeds. So no one can say that these are the design guidelines or a guidance to design the bicycles, because it's a highly empirical. There are lots of parameters are affect in the designs. So the most significant design detail is the geometric quantity called the mechanical trail to make the bicycle stable. So that we are going to discuss the effect of mechanical trails on our stability in a coming lectures or slides. You can look at this particular figure. So it shows many parameters. You look, this is a mechanical trail. This will be your steering axis. This will be the ground point contacts and this will be the steering axis. So the distance between the steering axis will touch the ground and a point of contact of the wheel with the ground is known as the trail. when you draw a perpendicular from the steering axis to the point of ground, this is known as the mechanical trail. This will be the head tube angles. This will be the center of gravity of bicycles. This will be the center of gravity of locations from the bottom base or a bottom wheel or back wheel, and this will be height center of gravity from the wheel base. It is also important to note that a bicycle does not have to be stable to be rideable. Skilled riders can balance on a stationary bikes, as we can see with the help of track stand methods, ride backwards, balance on one wheels, or ride a unicycle, and so forth. Also, virtually all bicycles have a low speed range of instability that riders routinely operate in, if only briefly. You might be facing this kind of issues when you are riding at very low speeds and you have to balance bicycles. So if only we can say that, however, stable bicycles will remain upright on its own without active control by riders, whereas an unstable bicycles require rider control to remain balanced. So that totally depends on your design, whether you design stable bicycles or unstable bicycles. Or you can make stable bicycles by unstable, make the stable bicycles by stable bicycle unstable by locking the steering mechanisms that we will see in the coming slides. So we can discuss a balancing on a bicycle. So a bicycle has only a 2 point of contact with the ground, and perpendicular from the mass center of machines and rider must fall on the straight line joining them. If a slight displacement will take place or some unstable or bicycles or riders be at rest, the position is thus one of the unstable equilibrium, and no amount of gymnastic dexterity will enable the position to be maintained for more than a few seconds. If mass centers will get a small displacement sideways, the displacement will get greater and the machine and rider will fall sideways. So in riding along with the road with a fair speed, the mass center is continuously receiving the such kind of displacement. If the rider steers bicycle in an exact straight line, this displacement will be get greater, and his bicycle will be overturned as when at the rest. When the machine is felt to be falling to the left hand side, the rider steers to the left, that is, he guides a bicycle in a circular arc, the center of which is situated at the left hand side, and thus they are making the bicycle stable. The centrifugal force due to the circular motions of a machine and rider now balance the tendency of the machine to overturn. We'll see a small video ride stably without the rider for a long distance.
Bicycles are amazing that you can balance them. Somehow you just on 2 narrow wheels you can keep them upright. And you can only keep them upright when they're moving. And what's well known about bicycle balance is that the major effect in bicycle balance is that steering is what gives you balance. If you lock the wheels of a bicycle so it can't steer, the angular momentum of the wheels contributes exactly nothing to bicycle stability, and it falls over when it's moving forwards exactly the same way it falls over when it's stationary. The amazing thing about bicycles is that they can balance themselves. That somehow a bicycle, if it's moving fast enough and not too fast, will steer itself and balance. And I balance this, and I can balance this with my hands. And the basic mechanism of the balance, if you want to think about it, is that when it tips this way, I move my hand back under this way. When it tips this way, I move my hand back under this way. And this is the basic mechanism for bicycle balance. So if you think of a bicycle rolling along and it's falling this way, the way that a bicycle balances is that you steer it And the steering doesn't do anything if a bicycle is not moving. But if a bicycle is moving forwards, when you steer it, it moves the wheel sideways. And the net effect is, I'll aim this at the camera, is if the bicycle's leaned this way and you steer it, it pops the wheels underneath the top of the bicycle. So it's as if I'm balancing the bicycle on my hand, and when the bicycle leans this way, you steering it brings the wheels back underneath. Steer it this way, it feels it brings back underneath. Now the natural thing to think of is that it's something about a gyroscope, so that you know that when things spin fast, they somehow are rigid because they're spinning. So here's a kid's gyroscope. And when it's spinning, think of it as a bicycle wheel spinning. It has a tendency to keep its alignment. So for example, it can balance. And you would naturally think that a bicycle is stable because of the spinning. And as I said, what we showed is that when you tied the handlebars and don't let it steer, this gyroscopic effect doesn't give any stability. So what is it about the moving that gives it stability is that this spinning gyroscope has this sort of squirrely aspect, which you can feel when you hold a gyroscope. It's not just that it wants to keep its alignment, it's that when you try to turn it one way, the effect is to turn a different direction. And the net effect of that is that for a bicycle wheel, if a bicycle wheel is spinning, so imagine this bicycle wheel is spinning like so, that when the bicycle tips to one side, this wheel acts like a gyroscope, and the net effect of this tipping is that it causes a steering. And then the result of that steering is that the bottom moves to the side, and the bottom and the wheels are brought back under the bicycle. So that's one of the explanations for how bicycles can be self-stable. It's a gyroscopic effect. The other claim about bicycle self-stability, how that can balance itself, has to do with the caster. So this is a caster, and what a caster is a wheel, but the wheel itself is mounted on something which has another axis. So where you see these, for example, is in the front wheels of grocery carts and on the bottoms of chairs and things like that. The job of this caster is that if you have some piece of furniture or grocery cart and it moves in one direction, the wheel follows around however you roll it. Now if you look at this thing, a bicycle in disguise is itself a caster, because here we have a bearing for steering, and here we have a wheel which rolls on an axle. If you look at the bicycle, it's got this bearing for steering and a wheel that rolls on an axle. It's got different size to it. Now this effect that the caster has, that it follows whichever way you move it, the reason it follows is because this wheel contact point is behind this pivoting or steering axis. And on a bicycle, this is a subtle bit of the geometry, but if you look at this steering axis, it comes down in a line like this, and it hits the floor about here, just under here, whereas the wheel contact is back here. So the calculations showed that neither gyroscopic or trail effects were important, and then Jim Papadopoulos designed on pencil and paper a bicycle that did not have these effects. I then gave the challenge to my friend Arne Schwab in the Netherlands, and he, with his student Jody Koyman, built one of these TMS, two-mast skate bicycles. So what it is, it's a funny-looking thing that looks maybe more like a scooter, but the idea is that it has no gyroscopic effect, no spin angular momentum effect, because it has two front wheels and two back wheels. The second front wheel doesn't touch the ground, it just spins backwards to cancel the angular momentum, and the second back wheel spins backwards to cancel the angular momentum. And it doesn't have this caster effect because it has the ground contact point actually slightly forward of the steering axis instead of behind the steering axis as in a conventional bicycle. And they pushed it, and it would balance itself, and they knock it sideways a little bit, and it would pop back upright, just like the calculations said it should do. It has to be that somehow leaning causes steering. But there are various mechanical effects besides the gyroscopic effect and besides the caster effect where leaning can cause steering. And the mechanism that bicycle has for being self-stable is that it has a mass in the front assembly which is forward of the steering axis, and it has a mass in the frame. And when the bicycle falls, this one tends to fall faster, just like if a stick falls and the stick is shorter, it falls faster than a longer stick. So this front mass falls faster than the rear mass, but they're connected to each other by the steering axis. So in its attempt to fall faster, it causes steering. And that's what we think is the primary mechanism of stability of this TMS, this gyro-free and trail-free bicycle. But there are other coupling effects that could contribute to self-stability of a bicycle. And they're in the equations, and they affect the self-stability in principle just as much as the gyro effect, the trail effect, or this gravity effect, which I just described.
So from this video, it clearly shows that when steering is locked, the bicycles fall quickly. While if we allow the bicycles to ride without the rider, it can be moved for some long distance in a stable manner, or it can gain its stability by its own.
If you're riding a bike and want to turn right, you might think that you should turn the handlebars to the right. However, that's wrong, because unlike a car where turning the wheels merely changes the direction the car is pointed, turning the front wheel makes a bike lean. When you turn the bike wheel to the right, the wheel goes to the right out from under you and the rest of the bike. So now you're leaning to the left, and the force on the bike from the ground will be directed to the left, and a leftward force, of course, makes you go to the left. Since physics seems determined that you're going to the left, you'd probably better just give in and let the handlebars turn to the left too. And that's how you turn left on a bike, by first turning right. If you really wanted to go right, you should have started by counter-steering to the left. Once you finally get yourself into a right turn, you'll also need to work to keep yourself in the turn, since most bikes and motorcycles have a tendency to automatically stabilize and straighten out on their own. This happens because a right-leaning bike automatically steers itself even farther to the right to get the wheels back underneath its center of mass, so you'll actually need to apply a slight torque to the left to keep the wheels from turning too far to the right. Yes, it's counterintuitive. To turn right on a bike, you turn left, then keep trying to turn left while leaning and turning right. Bikes are weird. This episode of
Seen in that video that how when we have to move in a curvature, so first if you want to take a turn in the left, we have to move right, and then we have to take a turn to keep a center of mass in a line segments. So we move further. So in fact, the expert riders automatically steer the bicycles in a circle of such a diameter that the centrifugal force slightly overbalances the tendency to overturn, and the machine again regains its perpendicular positions. If the track of bicycles can be examined, it will be found to be a not straight line but a long sinus curve. With beginners, the waviness of curve will be more marked than the expert riders, but even with the later riding, their straightest, the sinuosity is quite apparent. It would be possible to ride a bicycle in a perfectly straight line with the steering wheel locked by having the flywheel capable of revolving in a vertical plane at right angles to that of the bicycle wheels, and provide with a handle which could be turned by the riders. So like we seen in the one of the video that if when we when the steering will be locked, the cycle is falling very quickly. So to overcome this effect, if you want to move with the locked steering wheel locked bicycles, we have to add one of the flywheel. So that will be balancing the center of mass below the wheelbase, or you can say the straight lines. If the bicycle were falling to the right, the flywheel should be driven in the same directions. The reaction on the rider and frame of bicycle will be coupled, tending to neutralize that due to the gravity causing the machine to fall. But this is not like, this is just an example. So it is like, in reality it is difficult to drive a bicycle with the steering wheel locked. Lateral oscillation of bicycles. like from the previous explanations of the balancing on the bicycles, it will be seen that a machine and the riders are continuously performing small oscillations sideways, the axis of oscillations being the line of contact with the ground simultaneously with the forward motions. The aim of doing is, or aim of the oscillation is to keep the bicycle upright by balancing the center of mass. The bicyclist and his machines may thus be roughly compared to an inverted pendulums, just like the boomstick, as we seen in the one of the video that they are having the long sticks. A boomstick is more easily balanced in the hand than a pencil, because a boomstick having the large more length compared to the pencils. Similarly, a tall bike with a high center of mass can be easier to balance when ridden than a low one, because the tall bike's lean rate will be the slower compared to the small bikes. However, a rider can have the opposite impressions of a bike when it is stationary. Top heavy bikes can require more effort to keep upright when stopped in a traffic. For example, then a bike which is just as the tall but with a lower center of mass, you can make balance easily. A small force at the end of lever, the seat of handlebars at the top of the bike more easily moves a large mass if the mass is closer to the fulcrum, where the tires touch the ground, as we have seen that wobbles always wobble but never to be a fallen down. So if you have the tall bike where you have the low mass or low center of gravity or low center of mass of bicycles, then it is slightly easy to balance compared to the higher center of gravity. This is why touring cyclists are advised to carry a loads low on a bike, and panniers hang down on the either side of the front and the rear racks, so that they can keep the center of mass as much low as possible to make the bicycle more stable. So the time of vibration of a simple pendulum is proportional to the square root of its length, and a long pendulum vibrating more slowly than the short one. So that we discuss. In, you can say in other words, the angle of swing from the vertical is greater in the safety than in the ordinary. The track of an ordinary will therefore be straight, that is made up of the flatter curves than that of a safety, both bicycles being supposed to be ridden by a equally expert riders. Now we move to stability of tricycles. As already discussed earlier, that a tricycle having the 3 point of contact, so which forms a triangular base form and which can be statistically stable. But we have to see when we are riding the tricycles what should be the forces or moment to be created at the wheel base that might be topple the bicycles or tricycles. If you can look in the figure first, ABC be the points of contact of the three wheels of a tricycle with the ground. It will be the equilibrium under the action of rider's weight, provided that the perpendicular from the mass center of the rider and machine fall within the triangle of ABC. You can take this W will be the weight of a rider, and if we say that like a frame is the weightless, then if this W will be fall within this particular triangular, then and that bicycle will be stable. If this perpendicular fall at the point D, the you can say that this at particular D, because like it's a triangle, and if maybe because of the frame constructions, or we can add the weight of a frame in this particular analysis, and the perpendicular of weight fall at the point D, the pressure of the wheel on the ground can be easily found by the principle of moments. So we can say that B will be the total weight of rider and the machines, and WA, WB and WC are the pressures of the wheel at A, B and C on the ground. Then by taking the simply moment about the line BC, we need to draw a perpendicular A1 and D1 to BC, because right now we are calculating the pressure at wheel A and we are taking the moment at B and C. So the bicycle is now in a stable condition. So we can say that W into D1, because that W is acting at the point D and we take the perpendicular distance D1 is equal to pressure exerted at the wheel like ground support at point A into the distance, that is the A1. So from this we can easily calculate the pressure WA, that is the W into DD1 by A1. And similarly we can find out the WB and WC by taking the moment at different points. We can easily find out the WB and WC. Now if look, this point D will be the outside of this triangular ABC, because of the, or assume that a frame is made in such a way that when riders sit on a tricycles, the weight of a weight or a center of mass will be falling outside of the triangular ABC. In that case, the bicycle will be statistically unstable and will be topple over. Similar exercise will apply on stability of bicycles when we are moving in a particular circles. So you can see in a figure that a bicycle is moving in a circle, or you can say that moving in a curve. The same example is explained over here also. You can take, this is the bicycle. Now when it's moving in a circle, it's slightly lean towards the left or right, depends on the left curve or the right curve, or left turn or the right turns. So your center of mass is slightly lean by the angle, you can say theta L, or you can say this particular angles or angle, you can say that the angle is AL. So we discuss how the bicycle will be stable when we are moving in a circle. Let's assume that RT, or you can say that R will be the radius of circle in which the cycle is moving. W is the weight of rider and a machine, and the point Z at which the position of center of mass is there. We have seen that body of mass, you can say that WB, or you can take the M, moving in a circle of radius R with a speed of moving velocity V, has a radial acceleration that is equal to the V square by R, and it must be acted on the radial force, that is WV square by GR, or you can say that MV square by RT into G, because it will affect the gravity. Gravity is also acting on the particular points. Now considering the weight of rider and a bicycle, consider point G, and that is transmitted from G to the ground by a weightless frame. The only force acting on the frame are the weight W, which acting vertically downwards at the G, and the reaction from ground are the, you can take reaction is the R. So thus the resultant force of these two, weight acting at the center of mass and the reaction at particular point of contact, that R must be therefore equal to the horizontal radius force, that is equal to the WV square by GR, or we can say that MV square by G into RT. That is the balance force. So that equal amount of horizontal radial force, that is equal to the W V square by GR, required to give the mass the circular motions and line of actions of R must therefore be pass through the center of gravity, or you can say center of mass G. So when this reaction line R is passed through the center of mass point G, you can take this example over here also, then a bicycle is to be stable. If this will not pass to the point G, then bicycle may be a topple down. So when rider is moving steadily in a circle or in a stable motions in a circle, the machine must be inclined to an angle, that is, you can take CAB, or we can say that angle theta L. To the vertical, so that the reaction R from the ground may or must pass to the point G, or you can take the center of mass, and then bicycle will be the stable. Thank you. We will discuss Gauss effect in the next lecture. Thanks for listening.